All right, so we are going to combine two ideas of U-substitution with the fundamental theorem of calculus. All right, so remember, when we don't just have a simple power rule, we will need to use U-substitution to do the integration, all right? So there's two options, and it has to do with your limits, okay? So the original problem is always in terms of x, typically, or some variable, but when we do a U-substitution, remember we saw on the graphs that we can change those limits to match the variable. All right, so I'm going to show you the same problem. I'm going to show you both ways. Now, I don't think that one is better than the other. It doesn't avoid any of the work, especially with the trig functions, but what I think it does is it kind of saves time because we're not doing some complicated substitution at the end. That's just my own personal thing. Other people say, well, it's more elegant and it saves a little bit of writing. That's true too. Okay, so on the first one, we are going to do it without changing the limits, and you'll see what that looks like. So because I have a function here and I have a function inside, we are going to try U-substitution. Since that has a power, we're going to pick the inside expression. So du equals 2x. And I actually have 2x dx, so I don't even want to divide by the 2. Okay, so when I see the purple 2x dx, I can write just du. This is u to the third. And I'm just going to leave these as no limits, okay? Because I don't like to put numbers here if this is in terms of u and these are x limits, remember? So that's fine for now. So I'm going to do the power rule. So u to the fourth over 4. And then we would want to integrate because it's a definite integral. I'm also not going to put my limits here, okay? But I do like to show my notation to show that I am integrating. And I'm done. So now I'm going to plug u back in. So we get x squared plus 1 to the fourth divided by 4. And then now I could keep my same x limits. Okay? So technically what we need to do is substitute 2 into our function and then subtract when we substitute 0. So I'm going to continue over here. So when I plug in 2, I get 2 squared is 4, 4 plus 1 is 5, 5 to the fourth is 625 over 4. If I substitute 0, 0 plus 1 is 1, 1 to the fourth is 1, 1/4. So then I can subtract, which does reduce, and I'm going to see if that goes in evenly. It does. So 1, 22, so 5, and 24, so 6. Okay, so that would be my integral value. Remember, that's my signed net area, if you want what it actually stands for. All right, the second strategy, and that wasn't super long, we are going to change the limits. So you'll see what I mean. So I still need to do my U-substitution. I just want to kind of compare side by side how much work each strategy is. Once again, I don't have to divide by the 2, so that's du. That's u. And I'm still going to integrate and leave my limits off because those are x values. So I get u to the fourth divided by 4. And now when I go to put in my limits, I can actually add my numbers here because I'm going to add my u limits. So if x equals 2, remember we've seen how we change our variables. So 2 squared plus 1 is 5. And then if I substitute 0, 0 squared plus 1, okay? And so you saw we did have to substitute 5 and 1 eventually. Well, no, actually we didn't. We had to substitute 2 and 0 eventually. So now I can do f of 5 minus f of 1. So 5 to the fourth, 1 to the fourth. So Okay, so we end up with the same integral value because it is still the same original function. But what I like about the second strategy, especially when we get to trig functions or natural log functions, is we kind of do the harder work on a simpler part of substitution, if that makes sense. Okay. Notice it's not like this is much shorter, but I just think this is cleaner. And I'm pretty picky about the notation. Okay. All right, so now you get to go ahead and decide which strategy you want to do. If you want to substitute some of these in to your calculator, obviously example 4, we won't be able to. You can go ahead and check your answer on a calculator. Remember, you type in that function, do your calculate, and then you'll see if they match. Technically, it should be done by hand. All right, example number 2. And just so you know, I'm not going to show 2 strategies from now on. I always show the second strategy, just because that's my preference. So u is my denominator. So du. So I don't want that 2, so we can divide by it. Remember, you cannot divide by variables. So because these are being multiplied, I can substitute 1/2 du. And this is u. So I'm going to get 1/2 the integral of, well, that would be u to the 1/2, and I'm going to bring it up as a power, and times du. Okay, I'm going to leave my limits off because I could, I guess, change them now. So let's go ahead and do that. So root 5 squared is 5. 5 plus 4 is 9. 0 squared plus 4 is 4. Okay, if you don't change your limits on that step, you can just leave that blank. Okay, I would prefer it blank than for you to put in x limits on a u equation, if that makes sense. So let's integrate. We get 1/2, and then we add 1, multiply by the reciprocal, and we're going from 9 to 4. Now, technically, and I don't show this on my next step, but remember, we're going to substitute the upper limit and then substitute the lower limit. Okay, so next. So I just do this. So if I plug in 9, my 2's reduce. Remember, 1/2 means square root, so the square root of 9 is 3. Minus, substitute 4, the square root of 4 is 2, so 3 minus 2 is 1. My software should be coming next week, so I can't show you this on a graphing calculator on the screen yet, but it is coming soon. All right, example number 3. These are being added, so you have 2 choices. I don't have to use the area anymore. I can go ahead and just integrate these together. All right, so I do need to do a U-substitution though. Because these are being multiplied, I can pick either one. So I'm just going to pick u is equal to sine. But this would work if you picked u is equal to cosine. You would change some things, but we all end up at the same spot. So the derivative is cosine dx. Now, because these are being multiplied though, I want cosine times dx, and so this one is actually not working. So we will need to integrate these separately. It really depends on the function and things like that. So I don't just start by splitting them, but once I get my little u box, then it kind of becomes obvious if we need to or not. Okay. Other teachers tell you just split them from the beginning, but with certain functions, you might want to keep it. It just really depends. Okay, so on this part, keep in mind this dx was really at the end of that. So when we integrate 1, it's with respect to x. Okay, I want that to be pretty clear. So I'm going to go ahead and do this red first before I do my u substitution. So the integral would be x, and I don't have to change my limits because I want to keep it as x. So we're going to do f of, and I write this so you know that's really clear because this really has 2 different parts of integration. So when I substitute pi over 6, I get pi over 6 minus 0. Okay, on this part, we are going to add, and we're going to do our substitution. So this is u, and this is all du. So I'm going to integrate u. So I get u squared over 2. And then I'm going to change my limits. So now I'm going to do the sine of pi over 6. So remember, that's 30 degrees. So 1, root 3, and 2. So sine is opposite over hypotenuse. So my limit is 1/2. And then I'm going to substitute 0. The sine of 0, remember your wave, is 0. Those are my limits. Okay, so now those are u limits on a u function. So see how I can integrate completely different when they're adding or subtracting. And I like to keep them separate. So now we're really going to add plus f of 1/2 minus f of 0. So 1/2 squared is 1/4, divided by 2 is 1/8. Substitute 0. 0 over 2 is 0. So we get pi over 6 plus 1 over 8. Now, I'm perfectly fine with that. You don't really want a decimal answer. The answer could be written with an LCD. At this level, you just have to be flexible. All right, example 4. Well, I added these numbers in. So remember, x is your variable, which means that b and a are just numbers, like 5 and 6. It doesn't matter. So we're going to treat them like numbers when we use them. So u is equal to ax squared plus b. So du, that's a power rule. I would still bring that down and multiply. So 2a x to the first, and then the derivative of a constant is 0, so dx. Now, 2a is a number, and they're being multiplied, so we can divide. So we get 1 over 2a is equal to x times dx. All right, so we get x dx is going to be 1 over 2a, that's du, and this would be u to the 1/2. I'm going to go ahead and leave my limits off just because I want to integrate. I'm just excited. I don't know, okay? Just to kind of give you a different option. Now, because I know I'm going to integrate and then I'm going to plug in 2 different limits, I'm going to go ahead and do a bracket here. So we get u to the add 1, 3/2 times 2/3 from, now I'll plug in my limits. So if x is equal to 1, I would get a plus b. If x is equal to 0, I would just get b. Okay? So this can get multiplied. The 2's reduce. And so I get 1 over 3a. And then I'm going to do f of a plus b minus f of b. Okay? I just factored out that 1 over 3a instead of keeping it in both terms. It's really a choice. So I would get 1 over 3a, and then a plus b to the 3/2 minus, if I substitute b, b to the 3/2. Now, I can't cancel anything out because those are together in a parenthesis. I don't really need to redistribute, so this is a great answer. All right, we're going to kind of mix some of the properties with U-substitution and things like that. So this is f of 2x. Remember, this is like a composition. It really stretches your graph. It doesn't move it left, right, up, or down. But all of these are in terms of just x. So we want to do a mini U-substitution. So if u is equal to 2x, du is 2 dx. So 1/2 du equals dx. And so we saw this concept on previous assignments. So by substitution, I get 1/2 du u. But remember, these are x limits, and we want to change those to u limits, so everything's in the same term. So I get 1/2 f of u du, and if x is 2, u is 4. If x is 0, u is 0. And so I know this by substitution. So 1/2 of -8 is equal to -4. It really will work out mathematically to be equivalent. And that's kind of what we showed up here. Okay, so that's why if you are struggling before why it works, this was really the idea. I just couldn't explain it because we hadn't introduced U-substitution with the change of limits and the area, things like that. Okay. All right, same concept. So we're going to try u is equal to 1/2 x. du is 1/2. So multiply by 2. So we get 2 du u, and f of u du, we'll change our limits. If x is 2, 1/2 times 2, x is 0. And so by substitution, remember these are all dummy variables, we get this is 6, 12. All right, we saw this substitution on our first problem, so I'm going to go ahead and use that. So this was u, dx was 1/2 du. And so I want 1/2 if x is 2, 2 times 2, u is 4. If x is 1, 2 times 1 is 2, f of u du. Okay, so now we want to kind of use this knowledge. So I like to draw a number line. And I've got 0, 1, 2, and 4, and this is about f. So from 0 to 1, I know overall that's going to be 6. And I'm just going to assume it's all above. From 0 to 2, we know overall that's all going to be 4. And I know from 0 to 4, the whole thing, I know that's going to be -8. So I need to use that information because I need to know from 2 to 4, and we're not just given that. So I'm going to work backwards. So if I know this whole thing from 0 to 2, we can even make that an equation. So 6 plus x has to equal 4. That's really what we're looking at. So subtract 6, so x equals -2. So then I can make this like y from 2 to 4. So I know the whole thing is -8. So that has to add up to, this part was 4. And from 2 to 4 is y. So subtract 4. So y is equal to -12. Now, I know I didn't need to find from 1 to 2, but that could be on a different problem. So from 2 to 4, we just said that that was -12. So 1/2 times -12 gives me -6. Okay. All right, so on your assignment, I gave you 6 problems to try, and then I want to go over a little reminder of odd and even. This literally would have been probably one section, probably not even the whole day, where you talked about it. I reviewed it when we did limits. I don't think it came up in derivatives again, so it's always a good idea just to do a little bit of review. Since we are talking about areas, a lot of times the AP or just math questions in general will tell you some values and then they'll tell you something about the original function, that it's odd or even. So that has to do with the shape of the graph. And remember, that's your signed area. So that does affect something. So if they say that a function is even, what that means is that it is reflected about the y-axis. Okay, so if I had a graph and they told me this, and they said that that function was even, let's say it was f, well then I would know from here, so when I did that integral value, they would both be negative integral values, okay? And that's where this plays in. If a function was odd, let's say I took the same idea and they only gave me part of it, because that's what happens. Well, then I know that the function, it's going to have a 180 rotation. And so what it kind of means is it's the opposite side of the y-axis and the x-axis. So if this is in the fourth quadrant from 0 to A, then before it, it was above. Okay, and so what happens is those areas would be the same amount, but one would be positive and one would be negative, so then they would cancel each other out, and my integral value would be 0. This integral value would be double. And it would either be positive or negative. We don't know. Okay, so that's where that comes into play. So keep that in mind. Like I said, it doesn't come up very often, but it does on my problem, just to give you an idea. Okay, so then we can add more questions, more graphs, and combine it with area and integral values and things like that. So go ahead and give that a try, and good luck.